Hi, this is Mrs. Westmoreland, and this is a video lecture on solution stoichiometry for AP Chemistry. So I'm just going to talk through some of the example problems out of your notes packet. So in the first two examples, exercise 1 and exercise 2, we're given a mass of the solute. In number 1, it's grams of solid sodium hydroxide. And when we have mass of solute, we simply have to change that to moles of solute using the molar mass from the periodic table. And then we divide the moles of solute by the volume of the solution in liters to get the molarity. So in exercise 2, it's quite similar. We're given the grams of the solute, which in this case is gaseous hydrogen chloride, and we convert from grams to moles using the molar mass of the HCl. And then we divide the moles of the solute by the volume in liters of the solution, but you'll notice that in the question you're given the volume in milliliters, and so before you make that division you have to convert to liters because molarity is defined as moles of solute per liter of solution. Exercise 3, is just another application of that part within a whole mole ratio that we've been talking about quite a bit. And so when you have a solution and you know the molarity of the whole compound, you can apply those mole ratios from the subscripts of the compound to find concentrations of particular ions within the solution. So for example, in the 0.50 molarity cobalt to nitrate, since there is 1 mole of cobalt for every 1 mole of the solution, the cobalt concentration is 0.50 molarity. And you'll notice that to designate concentration, we use these square brackets. And then because there's a subscript of 2 after the nitrate ion, that means that the nitrate ion has 2 moles for every 1 mole of the compound. And so that's why its molarity is 2 times 0.5, or 1.0 molarity. Same is true of the iron 3 perchlorate in letter B. The iron is 1 mole for every 1 mole of compound, so it has the same molarity as the compound, and the perchlorate is a subscript of 3, so we have to multiply by 3 to get the concentration of that ion. Then exercise 4 is again looking at concentration of ions, but this time we are looking at not just in a 1 molarity solution or in a solution, but also in a particular volume of the solution. So for these kind of questions, you just have to remember that anytime you have a volume and a molarity, the molarity can be used as a fraction style ratio. So you can multiply your volume in liters times your fraction style ratio of molarity, which sort of expands to become moles per liter. And therefore your liters are going to cancel out to give you moles. And then in this case, since in the zinc chloride we have 2 moles of chloride for every 1 mole of the compound, we multiply by 2 to get the moles of the chloride ion. Exercise 5 also shows molarity being used as a fraction style ratio in your dimensional analysis. This time we're going from mass, 2 moles, and once we know the moles of the compound, we can use that fraction style ratio of the molarity to relate moles to volume of the solution. And this time you'll notice that the moles are in the denominator and the volume are in the numerator, because that's what we want to get, is the volume that would contain that mass of that particular solute. So it's just another connection to mole. It's another way to use the mole map of Moland. It's another relationship. Exercise 6 relates directly to what I was talking about in terms of preparing for the lab and creating that stock solution. So if I know the desired volume and the desired molarity of a particular solution that I want to prepare, then I can use those things to find the number of moles that I need of the solute, and then of course use the molar mass to figure out how many grams of that solid solute do I need to weigh out and dissolve in the particular size of volumetric flask to make my desired molarity. So again, we're using molarity as a fraction style ratio, which relates moles per liter. So even though molarity is written as 0.200 capital M, what that really means is 0.200 moles of solute for every 1 liter of solution. And then exercise 7 involves diluting. And anytime we are diluting solutions, we're using the formula or the equation molarity of the first solution times the volume of the first solution is equal to molarity of the second solution times the volume of the second solution. And essentially we're setting moles equal to moles in that case, because molarity times volume gives you moles. And it's just proportional. As the volume goes up, the molarity goes down. And for that reason, because it's proportional, it does not really matter whether your V1 and your V2 are in liters or in milliliters, as long as they are both in the same unit of measurement. In this case, my V2 is in liters, and so really what I get on my calculator is 0.0094 liters, but it just sort of makes more sense since we're going to be measuring that out with a pipette to express it as 9.4 milliliters. So it is absolutely essential in the previous example in number 2 that we use the volume in liters here when we're calculating molarity, and when we're multiplying volume in liters times molarity to get moles. But when we are using M1V1 equals M2V2, you can plug in both V1 and V2 as milliliters and it will work just fine. Thanks for listening.